What I have here is a simple start-stop station right here, push button start-stop, motor starter, and a simulated three-phase load, which would be a simulated motor. I'm using lights to show off the rotation of the magnetic field that makes the motors turn. Power into this circuit is being fed by a variable frequency drive. So I can reduce the frequency, speed the frequency up. Now, one of the first tests I'm going to do is verify I got control power coming into this circuit. So I measure right here on the hot to the neutral, and I got 24 volts of control power. So this is coming from a variable transformer that's right next here, so I can actually adjust the voltage. Now, the drive itself, let's turn the drive on. It is on. And I start the circuit right there. This kind of lights up. It lights up right there inside of a rotation. We can slow the rotation down. We can speed the rotation up. But if I slow it down a little bit, we can actually see the rotation of the magnetic field is clockwise. We are currently at 1 hertz. I'm going to bring this back up to 10 hertz. Simple number, 10 hertz. And if I go ahead and take a voltage measurement right here across the terminals from one hot terminal to the next, I basically have some 24 volts, 26 volts. But that doesn't always work too well because the meters don't always give you an accurate reading. So now when I go ahead and take another meter out here, turn the meter to volts, it's on our volts, it's on AC, and I go take a measurement on volts, what happens here now is I'm showing 106 volts. Which meter's right? We have one meter showing 106 volts. Okay, 106. And the other meter right there shows a little bit less. One meter shows 106 volts. The other meter, it shows 24 volts. The difference is one meter is going to be a true RMS meter and the other meter is an average responding meter. Not all meters read the sine wave. Every meter reads the actual sine wave that's sinusoidal, but not every meter will read sine waves that are modified by power conversion equipment. Downstream of a drive, the power conversion equipment, how that works is you have a sawtooth waveform, it could be a square waveform, it could be pulse width modulation. There's all kinds of these different ways to create sine waves. So in other words, the average responding meter won't give you a true reading. So anytime we use power conversion equipment, we have to use equipment right there and meters that can measure those types of waveforms. So here I have 105 volts phase to phase. The other meter showed 25 volts phase to phase. So the voltage is 1. But now we can also read frequency. So we could read hertz. So if I select this, I have my hertz frequency right there. Set up for hertz, for kilohertz. And I read the frequency. This is showing me right there that I'm at 20 hertz, 25 hertz, 20 hertz. And yet the drive itself shows 10 hertz. So there is a difference, again, which one is right. Well, the drive is a little bit off when it comes to frequency because this is referring to how the drive operates. The actual frequency is going to be a little bit different. So drives, frequency, we measure amps, we measure volts, we measure hertz. Here I'm going to demonstrate some voltage measurements. But at this point right there, notice my test leads aren't touching anything, and yet I get a reading right here on the screen. That's not damage to the meter. What that is the magnetic fields from the nearby equipment. Those magnetic fields can come from other equipment, fluorescent lights, just about anywhere. But when I hit the stop button, those numbers are going to drop down slightly. So it's the magnetic fields create an induction on these test leads. So around AC power, when measuring AC power, induction is common on the terminals. Now the AC power itself, when I measure, I'm going to measure the line side of this starter, and I'm going to measure right here roughly, well, 14 volts, 16, 8, 25. This is fluctuating on this because this meter is not designed to be reading downstream from a variable frequency drive. So what I have right up here is a frequency drive. And this drive right there is creating, well, changing the frequencies, as you can notice by the blinking lights. So some meters are going to be specialized and some meters are not. We get into this. So what I'm going to do here is I'm going to take my test leads out and bring up another meter. This meter is identified right there as a true RMS meter. I plug in my common, plug in my test leads, I turn this to AC voltage. Now when I take the AC voltage on this test lead, I take my measurements right up here and I'm seeing a little bit different voltage. But look at it fluctuate. Dial up the frequency, it's going to stabilize a little bit better. Should, but it's not. So let's take readings right here, definitely directly at the load. Well, mistakes 101. See this guy? It's on DC power. Now we're on AC power. Right here we got 109, 110 volts. It's fluctuating slightly. 110, 111 volts, fluctuating slightly. Roughly 110 volts. 110 volts. Roughly 110. I measure phase to ground. I'm getting about 63. So we got different readings here. But notice right there when I go to DC power, I try to take the same reading on DC and I'm not going to get any kind of stability because a meter set on AC power will not read DC. And just like a meter on DC will not read AC. So if the meter is auto-sensing, it works great. If the meter is not auto-sensing, well, you got to pay attention to the settings. Now, going back to the AC power, I'm going to measure the control voltage coming in. Control voltage coming in is 24 volts AC. I have that dialed in with my variable transformer. I have a variac or a variable AC transformer. So dial in 24 volts on control. And phase to phase here, the drive is putting out 110 volts. So I can control that voltage on that drive. If I drop this frequency down to where you can see the rotation quite clearly, and we go back to AC. Volts AC. You got a fluctuating voltage. The voltage is fluctuating with a high voltage of about 50. So we slow the voltage down, we really can't read it too easily. Now the difference here is this meter is a true RMS meter, so I bring the frequency back up. Let's take it up to 30 hertz. We're at 31 exactly on the nose. If I measure the voltage, we got 179 volts here, 178 volts, phase to phase. We have phase to ground. Measure it so you can see it. 103 volts phase to ground. But now, I take this meter right here, which is not true RMS. A different meter. It's not true RMS. Same make, same brand, put on AC power. And what we see right here, phase to phase, 125 volts, phase to phase. Phase to ground is 80 volts. 80 and 125. And yet we go back to our first meter. If I can make it set. We go phase to phase and we got 178 volts. One says 125, one says 178. Which one's right? Anytime we go downstream of power conversion equipment, such as a frequency drive, any kind of power conversion equipment, we have to be using what's called true RMS meters, otherwise the meter won't read correctly. Because what the power conversion equipment does is it changes the sine wave. It changes it from a sinusoidal wave to what's called pulse width modulation. It could be a square wave, it could be a sawtooth wave. There's all kinds of different waveforms. We get into that in the electronic circuits. But without a true RMS meter, you're never going to take the right measurements or get the right measurements when taking those meters, changing those meters. Well, that's voltage. Now, we can also take a current reading on this meter. So I'm going to take my meter right here and I'm going to turn my meter to the amp setting. Well, the amps is a separate switch here on top. We bring up the power again to a little bit. Let's go 10 hertz. And I'm going to take a reading, and the reading shows up right here in the screen. So if I clamp around this one, this meter, this one phase, one light, is drawing 150 milliamps, 0.15 amps. If I measure this light, this one is dropping down to 0.1820, 0.21, okay, 210 milliamps. And this light right here is drawing a little bit less, a little bit more actually, 0.20, 0.21, 210 milliamps. Why is it they don't draw all the same amperage? This is because of the resistance of the individual light bulbs. In a motor, it works the same way. If one winding starts to wear out and goes to ground, the insulation fails a little slightly, it's going to have a higher resistance or a lower resistance and draw more current. So the current's going to be very rarely going to be the same on all the loads. Now, bad move, I clamp around all three of these at one time. Ow, that's hot. I clamp around all three wires at one time. And what I'm going to get is 0 volts. I get the imbalance, not 0 volts, but I get the imbalance occurrence between all three. That's not a total current. 310 milliamps, 0.31. This is the difference, the imbalance in current, the difference in current between all three phases. So we got to be careful in how we measure. We only want to measure one individual wire or input at a time. One individual input. As I change the frequency, well, so do the currents change. So I can measure current, I can measure voltage. Now let's go ahead and stop this. Turn this off. I can even measure in ohms. Now we go back here to this lead, this meter, plug plug my test leads back in, and I change this meter to ohms. What I can measure is the resistance throughout the circuit. For example, on a troubleshooting process, if I want to check the coil of the motor starter, I just measure across the coil. This coil is 4.3 ohms. If this meter would read OL, that coil is burned out. But being that I do get a reading, that coil is good. Now that reading can range from about 3 ohms up to about maybe 1500 ohms, depending on the equipment. Now the individual loads, I can measure these too. I put one lead on the common, the ground, and I measure across this light bulb. This one's got a resistance of 53 ohms, 53.3. This one has got a resistance 51.5. And this one has got a resistance, a different resistance of 53, 52.7, 52.8. It's not stabilizing because I don't have a real good connection with my terminal tips. Point is, there's different resistances on each one of these loads, which means they're going to have different currents flowing through them. So I can go ahead and use the resistance, and it does make sense. Takes the readings. There's a resistance, but now I touch my test leads together. This 0.5 ohms and 0.6 ohms, the resistance of my test lead, I got to take that into account with every single measurement I take, because my test leads are adding to that resistance. Now, there's other types of things that can actually be tested besides just voltage and current. So let's go ahead and tip this down a little bit, point my camera in a little bit different direction, and we have different things. We'll test rotation in just a few minutes. So what I have now here is common things you find in industry. You've got different types of diodes, different types of equipment. So all this type of equipment right there is pretty much common wherever you see it and wherever you work. Now, let's get back to the basics right here. If I put my meter in place, hopefully everybody can see that fairly easy. What I have right here is what's called a silicone control rectifier. This is a large piece of an electronic circuit called an SCR. Okay, a lot of things like power conversion equipment, DC welders, drives will have electronic components this big. Okay, this one's burned out and broken, so I can't really test it. But just to point out, not all electronic components are going to be small. They are, some of these things, quite large. One of the most common tests we run is testing a capacitor. There's two ways to test a capacitor. One, if my meter's got a capacitor setting, I just simply turn the meter to capacitor. That works very well all the time. Again, any numbers shown on that screen is going to be the induction right there from local magnetic fields. I short the leads together, it shows me there's nothing. Now, how this works is there's a battery inside of my meter. There's a battery in there. And this battery is going to provide a small voltage to actually use for different circuits, such as capacitors. So if I put my test leads across the capacitor, the battery in the meter is actually charging the capacitor to 1 volt. This capacitor shows me it has a rating of 220 microfarads. So this is good for lighting the motors. Now I turn the capacitor around or reverse the leads, and I do this reading again. And what I get right there, it takes a minute, same reading, 220 microfarads. If that screen did not change and reads OL, this capacitor would be dead. If that screen read a standard low resistance, complete low resistance, OL or 1.0, this capacitor would be shorted out. So it's very easy to identify the capacitors. But here you get capacitors like this. These ones are kind of big. You see these in drives. If I go ahead and test this, it gives me a funny reading on the meter scale. In other words, this capacitor is so big the meter can't read it. This capacitor was 220 microfarads. This one right there is 120,000 microfarads. It's not what you see in drives. So is it good? Is it not good? Next way to test capacitors is turning meter ohms. Now how this works is this meter, when I'm on ohms, will discharge 1 volt on these test leads. Okay, so we use that 1 volt. Now I put the meter in one direction, what I'm getting right there on the meter is 6.17 megohms. I reverse the leads on the meter, and now I'm getting nothing. Well, what it is right there is this capacitor right there is reading as shorted. That 0,0 is bad. Now this reading right here with the megohms, this is a discharge resistor that's within that capacitor. So capacitors can be tested fairly easily. But now we can also do other tests on other things such as diodes. Simple, we go to the diode setting and this discharge is right there. Now we look on some types of these little diodes and you're going to see a lot of these are going to have a line. That line is the negative portion of that diode, referred to as a cathode. So now right there I put one lead of my meter to one side of the diode, one lead of the meter to the other, and look what I get. On the screen it says 0.55 volts. It doesn't say ohms, it says volts. The diode itself, all this does is it lets current pass one direction of the diode. If I turn the diode around, I get OL, no current flow. I turn the diode again, now we got current flow, we got voltage of 5.5 volts. So we can identify good or bad. Now some of these diodes can get kind of big. This one would be on a circuit board. You got things like this that are on circuit boards. We measure them the same way. One direction we have OL. On the cathode side, we got 0.5 volts. But then again, some of these diodes right there can get kind of big. This would be one that would be like on a small welder. Okay, different types. Again, it works the same way. I measure it from one lead to the other lead. I have OL on one direction. I have a voltage on the other direction. So we can identify diodes good or bad, but now how this works again is we don't always have diode settings on meters, so we can also use ohms. Now be aware the ohm setting only works well when the battery inside of the meter is good. If that battery in that meter is wearing out or low, it won't have enough voltage in there to turn the diode on. But what I do is I take a measurement from both ends of the diodes, and right here I'm reading, well, it looks like 14 megohms, 9 megohms. We've got a high numbers, 6 megohms, very high. Now we turn the lead around and now we're reading again, a lower reading, 0.6 megohms. So we get a low reading one direction, we get a high reading the other direction. Well, one direction you're going to have a high reading in megohms, and the other direction you're going to have a low reading. That's how diodes work. Measuring on ohms, it's going to be a low reading one way, a high reading the other way. And these diodes right there are just about everywhere. You find them in welders, you find them in equipment, you find them in alternators. You find them just about in all equipment today, anything that converts from AC to DC. So you can measure the diodes. I'll be posting a PowerPoint right there following this video showing you how these work. So we can measure things like the diodes, we can measure capacitors, we can measure things like frequency, and we can also measure the rotation of the circuits. So let's go back up over here to the equipment. Back up over here to the equipment. Bring this up a little bit. And I put my meter in here, and I'm going to set my meter to hertz. Frequency. Now I turn on my control power, and I measure my control circuit at 24 volts, and it shows me my control circuit is 60 hertz. But now I start my equipment right here and turn on my drive. If I try to measure this frequency right there on the drive, I'm over here at, looks like 19 hertz, 21 hertz. So even though that frequency right there on one of the drives says one thing, the measurement is a little bit different. Turn this down. Let's see if I can get down to exactly 1 hertz. We got 0.9 hertz. So right here it does match. We got 10 hertz, 0.9 hertz. So we can measure frequency. Now another measurement that has to happen one time or another, we stop, is we have to use a device like this, which is a rotation tester. Rotation testers are used all the time, guys. Now how this works is I'm going to go ahead and clip my leads on this tester right here on the terminals of the load. So this could actually be done in the side of a panel board. It could be done at the motor equipment itself. It could be done anywhere there's access inside of a disconnect switch, anywhere. When I go ahead and start the equipment, well, this little tester doesn't do anything at all or show me anything. But when I hit the test button right there, it's showing me that we have a phase loss for one. It's because I'm using a drive. But now we speed it up right there and that phase loss goes away. We're going to operate in reverse counterclockwise, but we do have a phase loss. And if I had a reverse direction of the drive, now running normal. But because it's a drive, it still registers a phase loss. What I'm doing with this drive and why a phase loss occurs is I have 120 volts, which is a split phase, single phase, converting it to 3-phase. So they do make equipment for this. So we got measurements of all types, guys. We can measure just about everything. Volts, AC and DC, ohms, amps, frequency, rotation, capacitors, diodes, LEDs. We can measure all of it. These are common measurements taken in the field. All we need to do is understand what we're doing and how we're doing it and have the meter that's the right tool for the job. We also identified different types of meters. For example, this meter right here is True RMS, right up here on the screen, True RMS. If I'm reading downstream of power conversion equipment, if I don't have True RMS, you don't get the right readings. This can be a nightmare in industry because you might be running correctly and you think you're having problems. So there's all kinds of meters, there's all kinds of ratings. Follow the meter's instructions, read the instruction book, stay safe. Diodes. Diodes are found everywhere throughout industry. They're in all kinds of equipment. Everything from welders to automation equipment, manufacturing equipment, cars, electronics. They're everywhere. The symbol for a diode is pretty straightforward. This diode right there has got a cathode. It has an anode. Okay, the arrow is the anode, the line is a cathode. Now a lot of these diodes right there, when you pick one up and look at it, will have a line on it. That is the cathode. The cathode is a negative polarity. The anode is a positive polarity. Now, the only thing this diode does is it allows current to pass only one direction through the diode. So that electrical current will not pass through that diode. It's blocked. It only allows electrical current in one direction. So the term technically is called rectification. It's a rectifier. Now, how the diode works is simple. If I apply an AC power to the diode, well, the diode only allows current flow in one direction, but AC power flows one direction, stops, reverses, passes in the opposite direction. So what's seen coming outside of the diode is only 1/2 of that sine wave. It only allows current to pass one direction. So diodes are pretty straightforward in how they work. Testing diodes doesn't have to be complex. There's a number of ways to do this. If your meter has a diode function, you turn the meter to diode function, but either way, the meter has to have a good battery into it. The diode function applies a voltage to the diode to turn it on. Now, the ohms function could also be used to test diodes. Okay, you read ohms by discharging 1 volt from the test leads onto whatever it is you're trying to read. And the voltage drop is actually the resistance. So it's kind of complex how the meters actually work like that, but we're using the battery or the meter on ohms, the battery in the meter to turn the diode on. So now if I measure right here the negative terminal, the common to the negative cathode, and I take the positive terminal, the red leads, to the anode. Okay, if that diode is good, I'm going to read right through that diode. And I'm going to see a low resistance, usually 0.3, 0.5, 0.7 ohms. It's a fairly low resistance. But if I take my test leads and reverse the test leads, now I'm going to have a very high resistance. Meter might read OL or it might give a high resistance. Typically it's around anywhere between 10 and 30 million ohms or mega ohms. So you get a low resistance one direction, swap the leads, a high resistance the other direction. Now if I take a measurement on that diode, negative to the cathode, positive to the anode, and I read OL, that diode is burned out. Either the battery in the meter's weak or the diode's burned out. And if I take a measurement swapped around and I get OL, again, either the battery's worn out or the diode's burned out. If I measure cathode to anode, negative to positive, and I read 0.0, the diode is shorted. So there's nothing to actually turn on or off, it's just passing current straight through. If I measure backwards from cathode or anode to cathode, negative to positive, positive to negative, and it reads 0.0, again the diode is shorted. So diodes don't have to be complicated, but they are found all throughout industry.